Okay, good day class. So welcome to our online lecture on for the subject general mathematics. So in this lecture, in this video, our highlight is on the piecewise defined function. So at the end of the lesson, you should be able to define a piecewise function, evaluate a piecewise function, graph a piecewise function, and then find the domain and range of a piecewise function. So let's start by answering this pre-assessment activity. So the following equations are subfunctions of a piecewise function f of x. So letter A, f of x is equal to 3x plus 1 if x is greater than 0. F of x is equal to 4x plus 2 if x is equal to 0. And then f of x is equal to 5x plus 3 if x is less than 0. So identify the equation that will define the function at the given value of x if our x is equal to 4, x is equal to negative 1, x is equal to 0, x is equal to 3, and then x is equal to negative 6. So you may pause this video and then resume after you finish answering these pre-assessment questions. Okay, so before we discuss the answer to these pre-assessment questions, so what can you notice about the given functions? So if we look at our functions here, f of x is equal to 3x plus 1 is equal to 4x plus 2, f of x is equal to 5x plus 3. All of these functions are functions that define the same function. So these three defines the same function f. So therefore, we can rewrite this as f of x is equal to 3x plus 1 is equal to 4x plus 2 and is equal to 5x plus 3. So we have here three functions that define the same function f. So now that we have multiple function that defines the same function, how can we now know when will this function 3x plus 1 is will be used to define our function f? When do we use 4x plus 2, and then when do we use 5x plus 3 to define our function f? So to know when to use these functions, we need to look at the given interval of domains or interval of x. So it is mentioned in our given that our function f of x is equal to 3x plus 1 if our x is greater than 0. So f of x is 4x plus 2 if our x is equal to 0, and then our function is equal to 5x plus 3 if our x is less than 0. So I hope you already have an idea on what is a piecewise function. So before we discuss the answer to this pre-assessment, so let us first define what is a piecewise function. So a piecewise function is a function defined by more than one equation. So where each equation applies to a certain interval of the function's domain. So here we have our representation. So our main function is our function f. So f of x. So f of x is defined by two subfunctions in this representation, but a piecewise defined function can be defined by two or more subfunctions. So here we have our subfunction number 1, and we also have here our subfunction number 2. So these subfunctions can be different types of functions. Let's say, for example, the first subfunction is linear, the second function is quadratic, or maybe they are both linear, they are both quadratic, or maybe there are other types of function that defines our piecewise function. So this subfunction or this equation, this subfunction, is applied to a certain interval of domain. So we have domain 1. So this domain serves as our conditions so that we know when will our function f be defined by subfunction 1, when is our function is defined by subfunction 2. So we need to look at the value of the domain. We need to look at the conditions and the given value of x. So the domain and range of a piecewise function is the union of all the smaller domains and ranges. So since we have two or more subfunctions, and these subfunctions have different equations, therefore there are different values of domains, there are different intervals of domains and range that can be applied to these specific subfunctions. So to get the domain, we need to get the union of the domains of these different subfunctions, and to get the range, we need to get the union of the ranges of these subfunctions. So later on, we will have a step-by-step procedure on how to determine the domain and range of a piecewise defined function. So the definition of a piecewise function changes based on the value of the domain. So that is why it is very important that in a piecewise defined function, we pay a closer attention to the value, to the given value of x, and then compare it to the given conditions for each of the subfunctions, because the given value of x helps us in identifying the equation that defines our piecewise function. So if we go back to our pre-assessment, so we have three subfunctions here, and we can rewrite it as f of x is equal to 3x plus 1 if x is greater than 0, 4x plus 2 if x is equal to 0, and then 5x plus 3 if x is less than 0. So for item number 1, the given value of x is equal to 4. So we know that 4 is a value that is greater than 0. So if we compare it to the three conditions of our subfunctions, then we know that our given value of x is greater than 0. So thus, we use our first subfunction, f of x is equal to 3x plus 1, since our given is greater than 0. So this is our condition. So for number 2, our given value is a value that is less than 0. So negative 1 is less than 0. So what do you think is the answer? Okay, so that is correct. So letter C. So letter C is the answer for number 2. Since the given value of x is less than 0, then the function that will define our piecewise is f of x is equal to 5x plus 3. For number 3, since it is equal to 0, we use subfunction number 2. So f of x is equal to 4x plus 2. So if our x is equal to 0, because 0, we know 0 is equal to 0, of course. And then, for number 4, our given value of x is greater than 0. So thus, we use subfunction number 1 to define our function f. And then for last item, our f of x is equal to negative 6. Our x is equal to negative 6. So therefore, we use subfunction number 3, wherein our f of x is equal to 5x plus 3. So this, by comparing the value of our x to the conditions, we will be able to identify which of the subfunctions is to be used in order to get the value of our function. So with this knowledge, we can now evaluate our piecewise function. So in evaluating a piecewise function, first we determine to which interval of the domain does the given value of x lies, and then we evaluate using the corresponding sub-functions. So again, to review on the um, evaluating a function. So when we say to evaluate a function, we are looking for the value of the function. So let's say, for example, function f of x. When we are evaluating, we are looking for the value of our f of x. So by substituting the variables, so let's say, for example, variable x, by substituting all the variables with the given value. So example, so evaluate the piecewise defined function given the following values of x. So our piecewise function is f of x is equal to 3x plus 1 if x is greater than 0, f of x is equal to 2 if x is equal to 0, and f of x is equal to 5x plus 3 if x is less than 0. So evaluate if our x is equal to 4, if our x is equal to negative 1, and then if our x is equal to 0. So if we look at the given, our value x is equal to 4 is a value that is greater than 0. So thus, we use our first sub-function. So f of x is equal to 3x plus 1. So, but after identifying the sub-function to be used, we can now proceed with the evaluation of the function. So just simply substitute all the variables with the given value of x. Thus, we have f of 4 is equal to 3 times 4 plus 1. So f of 4 is equal to 12 plus 1. And then our answer to this problem is f of 4 is equal to 13. For letter B, so negative 1 is a value that is less than 0. Thus, we use our third subfunction, f of x is equal to 5x plus 3. So proceeding with the evaluation of function, we substitute all the variable x with the given value of x. So f of negative 1 is equal to 5 times negative 1 plus 3. So negative 5 times negative 1 is negative 5 plus 3 will give us negative 2. So f of negative 1 is equal to negative 2. And for our third problem, so our value of x is equal to 0. So at x is equal to 0, so we know that 0 is equal to 0. So thus we use our second subfunction, f of x is equal to 2. And then to evaluate, substitute all the variable x. So f of 0 is equal to 2. So whenever our x is equal to 0, the function is equal to 2. So again, if we look at this subfunction, so whenever our value of x is greater than 0, we use 3x plus 1. Whenever our x is equal to 0, we use f of x is equal to 2. Whenever our x is less than 0, we use 5x plus 3. And this is for this specific piecewise defined function. So now I would like you to answer these practice exercises. So solve for the value of the piecewise defined function at the given value of x. For numbers 1 and 2, so our given piecewise is f of x is equal to x plus 2 if x is greater than or equal to 0, and then negative x squared plus 2 if x is less than 0. So find f of negative 3 and f of 2. And then for numbers 3 and 4, so f of x is equal to negative 4 if x is less than 0, and f of x is equal to 2x if x is greater than 0 but less than 2, and then x squared if x is greater than 0. So find f of 1 and then f of negative 6. So you may pause this video and then resume after you answer the problem. Okay, so let's answer number 1 and number 2. So our given function is f of x is equal to x plus 2 if x is greater than or equal to 0, and then f of x is equal to negative x squared plus 2 if x is less than 0. So for number 1, the given value of what we call this, so the given value of x is negative 3. So negative 3 is a value that is less than 0. So therefore, from our subfunctions, we know that we need to use our second subfunction, f of x is equal to negative x squared plus 2 if our x is less than 0. So substituting, so f of negative 3 is equal to negative times negative 3 squared plus 2. So f of negative 3 is equal to negative times 9 plus 2. So negative 9 plus 2 is equal to negative 7. So f of negative 3 will give us negative 7. So for item number 2, so our given value of x is 2. So 2 is a value that is greater than 0. So therefore, we use our first subfunction. So f of x is equal to x plus 2. So substituting our function, so f of 2 is equal to 2 plus 2. Thus, f of 2 is equal to 4. So this is for our first two problems. Okay. So did you get both of all of the correct answers for our problems 1 and 2? So let's now proceed with problem number 3 and 4. So again, for our problem number 3 and 4, so our piecewise function is f of x is equal to negative 4 so if our x is less than 0, and then 2x if our x is greater than 0 but less than 2. So greater than 0 but our x is less than 2. So this is 2. And then our f of x is equal to x squared if x is greater than 2. So what we would like to find is the value of our function if our x is equal to 1 and if it is equal to negative 6. So for number 3, f of 1, and for number 4, f of negative 6. So to answer, so 1 is a value that is greater than 0. So therefore, we know, so greater than 0, but it is also a value that is less than negative 2. So 1 is also less than negative 2. So therefore, we know that 1 is greater than 0 but less than 2. So thus, we use our second subfunction f of x is equal to 2x. Substituting, so f of 1 is equal to 2 times 1. So f of 1 is equal to 2. For number 4, so f of x, our x is equal to negative 6, and negative 6 is a value that is less than 0. So thus we use our first subfunction f of x is equal to negative 4. So substituting, so f of negative 6 is equal to negative 4. So as you can see, we have here values and this given value of x, and to evaluate, we need to compare our given value of x to the conditions, to the given intervals of our domains, and then we need to look at the interval where our given value lies. So for example, 1 lies in between 0 and 2. So therefore, we know that our subfunction number 2 is to be used. So negative 6 is a value that is less than 0. So we know that negative 4 is our subfunction to be used. So f of x is equal to negative 4. And if our value is greater than 2, if our given value of x is greater than 2, then we know that the function to be used is x squared. So for example, we have a value of x that is equal to 3, then we know that our f of x is equal to x squared. So therefore, f of 3 is equal to 3 squared, and f of 3 is equal to 9. So we need to compare the given value of x with our conditions or intervals of domains. So now, what if in our given function, the given value of x is equal to 2? So what would be the value of the function f of x? So if we look at the value, so f of x is equal to 2. If we look at the conditions, so x here is a value that is, so for our first subfunction, excuse me, so for our first subfunction, the value of x are values that is less than 0. For our second function, the value of x is greater than 0 but less than 2. So we know that 2 is not included. And then in our third subfunction, our value of x is a value that is greater than 2. So we know that here 2 is also not included. So what if our given value of x is a value that is not included in our intervals of domains in the condition? So what will be the value of the function? So the answer to that is that the function will not produce an output at x is equal to 2, since 2 is not a part of the domain. So therefore, so f of 2 does not exist because 2 is not part of the domain of our given piecewise defined function. So in our previous lessons, we learned that not all of the values can be part of the domain and range of a function. So in this example, 2 is not a part of the domain of a function. So therefore, we don't have a value if our x is equal to 2. So let us now move on to graphing a piecewise of function. So you may try this. So pause this video and then resume after you answer these practice problems. So before we discuss the answer to this practice problem, so let us first learn how do we graph a piecewise of function. So graphing a piecewise function, first we need to identify the type of functions of our subfunctions. So our piecewise is defined by different subfunctions, so 2 or more subfunctions. And these subfunctions is not always the same. So for example, f of x can be defined by a constant function, or it can be defined by an identity function, or maybe a linear function, or it can also be defined by a cubic function. Let's say for example, x cubed plus 2x squared plus 3, or maybe a quadratic function, or other types of function. And we know that these different types of function has different graphs. So a constant function, the graph of a constant function is a horizontal line. So identity function is a diagonal line that always passes through the point of origin. So linear function is also a diagonal graph. So cubic function has 2 turning points. A quadratic function is a parabola. So therefore, it is important that you identify the type of function that of the different subfunctions, because the following step is for you to graph these subfunctions according to its type. So different types of functions has different ways of graphing it. So you need to review on how to graph. Let's say for example, how do we graph a quadratic? How do we graph a constant function? How do we graph a linear function? So you need to review on on the process, on the steps on how to graph different types of functions. And then um, third is limit the graph according to the intervals of the domains of the subfunction. So later on we will know how do we limit the graph of our subfunctions. And last is we need to apply the conventions on sketching the graph of a subfunction. So we learned that the graph of in the graph of a function, there are sometimes a hole in the graph, sometimes there are the endpoints, or along the graph there are shaded circle. There are also sometimes the endpoint of the graph is ended with an arrowhead. So we need to review on the different conventions of graphing a function. And then don't forget to label each graph, because we have different subfunctions, so therefore different graphs represent the same, I represent different function. So the graph of a piecewise function are all in the same Cartesian plane. So if we have a Cartesian plane, let's say for example this is our Cartesian plane, so let's just suppose that one of the function is graphed in this place, one of it is here. Let's say for example, so the graph, so this is our, let's say for example that this is our function subfunction number 1, and then this is our subfunction number 2. So the graph of a piecewise defined function is sketched in the same Cartesian plane. So that is why in our previous in our steps we include here label each graphs, because each of these graphs represent different subfunctions. Okay, so let us answer our practice problem. So we have here for our piecewise function number 1, so f of x is equal to x if x is less than 0, and then f of x is equal to 2 if x is greater than 0. So before we sketch the graph of this piecewise, let us first review on what is the graph of a of f of x is equal to x. So and then f of x is equal to 2. So first, f of x is equal to x. So f of x is equal to x is an identity function. So we know that the graph of an identity function is a diagonal line which passes through. So if we have here our Cartesian plane, so this is 1, 2, 3, so the graph of an identity function is a diagonal line which passes through the point of origin, and whatever is the value of your x, let's say for example 0, it is also the value of your y. So if it is 1, then the value of the function is also 1. If it is 2, then the value is also 2. So therefore we know that this is how the graph of an identity function looks like. So this is if our function is f of x is equal to x. However, in the definition of a piecewise defined function, we have an interval of x which serves as a condition. So since we have a condition here, sabi dito, it states here that our function f of x is equal to x if and only if our x is less than 0. Therefore, we need to identify the part of the graph where our x is less than 0. So let's use another color here. So in this part of the graph, so where is 0 located? So 0 is located here at the point of origin. So from this point to this point, we know that our x is greater than 0. But from this point, moving towards to this point, our x here is less than 0 because the values here is negative 1, negative 2, negative 3, and so on. While here we have 1, 2, 3, and then so on. So if we look at the condition, which do you think, which part of the graph should remain and which part should be discarded? So which should we remove? So is it this part of the graph or is it this part of the graph? So since our condition for our identity function f of x is equal to x is x is less than 0, therefore we need to remain or retain this side of our graph. So this is our 0. And then don't forget to apply the convention. So identify also whether this point here, whether this 0 here is an included or not included value. So since x is less than 0, then we know that 0 is not included, because if it is included, then the statement should say that x is less than or equal to. So we need to use this one. But since it is only less than 0, therefore 0 is not included in the domain of your identity function. So if we sketch that in our Cartesian plane, we have this line. So f of x is equal to x if x is less than 0. So this is our 0, where 0 is not included. Okay, so this is our 0, where 0 is not included, and this is the part of the graph where our x is less than 0. Okay, so how about f of x is equal to 2 if x is greater than 0? So f of x is equal to 2 is a constant function. Okay, so if we recall, the graph of a constant function is a horizontal line. So whatever is the value of your x, whatever is the value of your x, the value of your function f of x will always be equal to 2. So therefore, if we graph this one, if this is our Cartesian plane, and this is our f of x or our y, this is our x, so this is 1 and then 2. If we graph this function f of x is equal to 2, then this is how it will look like: a horizontal line where our function is equal to 2. So whatever is the value of your domain, the value of y is always equal to 2. However, in the piecewise defined function, the function f of x is equal to 2 will only be true if our value of x is greater than 0. So take note, greater than 0. So 0 is not included also. So if x is greater than 0, so locate this one in your graph. So 0. So 0 is at the point of origin. So this is 0. So which part of the graph is greater than 0? So let's change again the color of our pen. Okay, so this side of the graph, so from this point, so from this point, so this is our 0. From this point to this, moving towards this direction, the value of our x here is greater than 0. While from this point, the point of origin, moving towards this direction, the value of x is less than 0. So in our condition, f of x is equal to 2 if x is greater than 0. So therefore, we need to retain this side of the graph. And since 0 is also a not included value, then we make a hole in x is equal to 0. So thus the graph will look like this one. And our last step here is to label the graph of your subfunction. So this part of your graph is the graph for f of x is equal to x, and this part of the graph is our f of x is equal to 2. So you can also use different colors to represent the different subfunctions. So at 0, or at x is equal to 0, we do not have a value because 0 is not part of your domain. So this is not included value. Okay, so how about for number 2? So f of x is equal to 3, and then f of x is equal to x plus 3. So if x is less than 1 and x is greater than 2. So again, for f of x is equal to 3, so we know that this is a constant function, and we just simply need to apply our condition. Okay, so for the constant function f of x is equal to 3, so we know that in our Cartesian plane, this will be plotted in this, where our y is equal to 3. But then the condition says that f of x is equal to 3 if and only if our x is less than 1. So we need to locate 1 in our, we need to locate x is equal to 1 in our horizontal axis. So this is 1, 2, 3, 4. So this is where x is equal to 1. So it states here that f of x is equal to 3 if x is less than 1. So less than 1 is this part of your graph. So here x is less than 1. And then in this section of the graph, x is greater than 1. So therefore, we need to cut our graph. We need to limit our graph where our x is less than 1. And since 1 is not included, because it states here it is less than 1, therefore 1 is not included, we create a hole where our x is equal to 1. So thus the graph of our first subfunction f of x is equal to 3 is at this part of, so at this region. So x is equal to 1, where 1 is not included, and then less than 1. How about for our second subfunction? So f of x is equal to x plus 3. So how do we now graph this one? So this is a linear function. So in graphing a linear function, we need to look at the slope. So the slope, so here, so we can rewrite this as 1 times x plus 3. So the slope is 1 over 1. So m is 1 over 1. And then our y-intercept is equal to 3. So in graphing a linear function, we need to identify the slope and the y-intercept. So first, in graphing a linear function, locate the y-intercept. So let's say, for example, if we have this Cartesian plane, so y-intercept is equal to 3. So this means that the first point here is where y is equal to 3 and x is equal to 0. So the slope is 1 over 1. So slope is defined as rise over the run. So here we have 1 rise and then 1 run. So tataas tayo ng isa, we will move upwards by 1 and then move to the right by 1. So therefore, this is our second point. So to create the graph of this one, simply connect the line of simply connect these 2 points. So this is the graph of f of x is equal to x plus 3. However, we also have a condition. So this is only true if x is greater than 2. So now locate in your x-axis, locate x is equal to 2. So this is x is equal to 2. And then identify the region where x is greater than 2. So this is the part where x is greater than 2, and this part is where x is less than 2. So therefore, when we graph, we need to remove this part of the graph and then retain this section of this graph. Also, don't forget the convention. Since our 2 is not included in the domain because this is greater than 2, then we create a hole where our x is equal to 2. So if we look at the final graph now, so we have here f of x is equal to 3 if x is less than 1, and then f of x is equal to x plus 3 if x is if x is greater than 2. Okay, so what about if our subfunction is a quadratic? So how do we graph a quadratic function? So just for a simple review on how to graph a quadratic function, so suppose we have the equation x squared plus two x plus 3. So this quadratic equation is in the form a sub x plus b a sub x squared plus b sub x plus c. So the first step in graphing a quadratic is we need to find the vertex of the quadratic. Find the vertex. So the vertex is given by the coordinate h, k, where our h is the x coordinate and k is our y coordinate of the vertex. So the formula in finding the h is equal to negative b over 2a, and then the formula for k is equal to negative b squared minus 4 times ac divided by 4 times a. So we can just look for the value of h and then use this equation, so this equation, to solve for k, or we can use both of this formula to solve for h and k. So I'm just going to solve for h and then later on use this given quadratic equation to solve for the value of k. So to solve for h, just simply substitute. So what is the value of b? So from our equation, from our given quadratic, so a is equal to 1, b is equal to 2, and our c is equal to 3. So therefore b is 2. And then our divided by, so negative 2 divided by 2 times a, so a is equal to 1. So therefore negative 2 divided by 2 is equal to negative 1. So our h is equal to negative 1. So I can just use this value of h and then use this quadratic equation, given quadratic equation, to look for the value of the vertex k. Or I can use this formula for k to look for the value of k. So step number 2, second step, is to find k. So let's create a table of values. So our vertex is -1, and then we're looking for the value of k. So let us put here 2 points below 1 and then another 2 points above 1. So substituting the equation, f of -1 is equal to negative -1 squared plus 2 times -1 plus 3 will give us 1 plus -2 plus 3 will give us -2 -1 plus 3. So f of -1 is equal to 2. Therefore, therefore our k, the value of k is 2. So let us assign points to the left and to the right of our vertices. So let's suppose from one point to the left of our x is -2, and then another is -3, and here we have 0 and then 1. And then we need to evaluate to find the corresponding value of y for these values of x. So f of -3 is equal to x squared plus 2x plus 3. So f of -3 is equal to -3 squared plus 2 times -3 plus 3. So f of -3 is equal to 9 plus -6 plus 3. So f of -3 is equal to 9 plus -6 is 9 plus -6 is 3 plus 3 is equal to 6. For f of -2, so -2 is squared plus 2 times -2 plus 3. So f of -2 is equal to 4 plus -4 plus 3, and then f of -2 is equal to 4 plus -4 is 0 plus 3 is equal to 3. So therefore the value here, so -3, and the value of y is 6, and then for -2 the value of y is 3. And by the virtue of symmetry, so we know that the graph of a quadratic is a parabola, and at the vertex, that is the axis of symmetry. So whatever is the value of the points to the left of our vertex is the same doon sa kabila. So therefore, so here for -2, 3. So 1 point to the right of our vertex, 0. The value of y is also 3. And then here, the value of, for 1, x of 1, the value of y is also 6. So if we now graph this one, this is our graph. So this is 1, 2, 3, 4, 5, 6, 7. And this is -1, -2, negative 3. This is 1, 2. So at point negative 1, the value is 2. Negative 2 is 3. Negative 3 is 6. Sorry. Sorry. So at 2, it is 3, and at negative 3, it is positive 6, and then for 0, it is also 3, and then for 1, it is also 6. So this is, so I hope I would be able to draw a perfect parabola, but anyway, so this is a curve. So we know that this opens upward because our leading coefficient is positive. So now, let's suppose that there is a condition. So if the condition is that f of x is equal to x squared plus 2x plus 3, if x is greater than, so let's say x is less than or equal to 0, then we need to remove this part of the graph and only retain this one, and 0 is included because equal to 0, so we need to retain this part of the graph and remove this part of the graph, because this is where f of x, this is where x is less than or equal to 0. Let us now go to the domain and range of a piecewise function. So the easiest way to find the domain and range of a piecewise function is through inspection of its graph. So if you already graph your piecewise function, then by examining the graph, you would be able to identify what is the domain and what is the range of a piecewise function. So in determining the domain and range of a function, so you can take note of the following. So first, graph the piecewise and then examine the endpoints of the graphs. So in our previous discussion on the domain and range of a function, we learned that there are different endpoints of graphs. So sometimes the endpoint could be a hole, sometimes could be a shaded circle, and sometimes it could be an arrowhead. So we know that if it is a hole, or if there is a hole, then that the corresponding value is a value that is not included. If there is a shaded circle, then the value is a value that is included in the domain or included in the range. And if we have an arrowhead as an endpoint, we know that our value is moving towards the positive or the negative infinity of x and y. So we can also use the vertical line test for finding the domain and the horizontal line test for finding the range. The vertical line test and the horizontal line test also helps us in determining whether there are any discontinuities in our graph. So for example, if we have a graph, if our graph looks like this one, let's say for example, and then we have a hole in this graph. So of course, and then another one, let's say for example that the second graph of our piecewise is this one. So let's say for example that this is at x is equal to negative 3. So if the vertical line test, if we look at the vertical line test, VLT, this dotted line here, at x is equal to negative 3, there is a hole in both of our graphs. So therefore, we know that x is equal to negative 3 is not part of the domain. So vertical line test is used for finding in determining the domain and the discontinuities in our domain, and the horizontal line test is for determining the range and if there are any discontinuities in the range. So our next step is for us to write the domain and range from the lowest possible value to the highest possible value. So when we are determining the domain and range of a function, we need to start at the lowest possible value. So let's say, for example, that this is our Cartesian plane. So the lowest possible value of x will start at the negative infinity of x. So you need to look from this side towards this side when you are determining the domain of a function. And when you are determining the range of a function, so this is the negative y, this is the positive y, you need to look at the lowest possible y value, so meaning from negative y to positive y. We also have a rule for determining the domain and range of a function. So whenever two or more subfunctions of piecewise share the same value of x, x is a domain of the main function if it is included as a domain of all the subfunctions, or it is included as a domain of at least one subfunction. So what does this mean? So sometimes, so there are cases in a piecewise function where our subfunction shares the same value. So let's say for example, this one, our subfunction 1, and then we have another subfunction number 2. So let's say that this is x is equal to 2, and then this one here is y is equal to 5. So let's say for example we have this graph of our piecewise, and then so here at this point, so this is at x is equal to 2, and then so this is our Cartesian plane, let's say for example this is our Cartesian plane. So if we look at this graph, so according to this rule, whenever two or more subfunctions of piecewise share the same value of x, x is a domain of the main function if x is included as domain of all of the subfunctions, or it is included as a domain of at least one of the subfunction. So if we look at this graph, so at x is equal to 2, so for our subfunction 1, so let's say this is subfunction number 1 and this is our subfunction number 2. So in our subfunction number 1, x of 2 is not included because we have here a hole. So in subfunction number 1, so this one here, x of 2, x is equal to 2 is not included because we have a hole in our subfunction number 1. However, if we look at the graph of the subfunction number 2, we have here a shaded circle at x is equal to 2. So according to this rule for the domain, whenever two or more subfunctions of piecewise share the same value of x, so here x is equal to 2, and then this is also x is equal to 2. So x, that specific value of x, is part of the domain of the main function if it is included as a domain of all of the subfunctions, or at least one of the subfunctions. So since in f of 2, x is equal, in our subfunction number 2, x is equal to 2 is included, therefore in the main function, x is equal to 2 is also included in the domain. So 2 is part of the domain of your function. So this is true also to y. So this rule also applies to y. So whenever two or more subfunctions of piecewise share the same value of y is a range of the domain. Y is a range of the main function if it is included as a range of all of the subfunctions, or it is included as a range of at least one subfunction. Go back to our previous graph. So here. So if we look at this point, let's say this point is 3. Let's say this is 3. So that this part here is 3. So let me just... So let's say that this is 3. So in our first graph, so the graph of our subfunction 1, 3 is an included value. In our graph number 2, 3 is also included. So we have here a solid line. So therefore, since both of these are, since 3 is part of both of the subfunctions, then 3 is an included value. And then if we look at y is equal to 5, for our graph number 1, for our graph of subfunction 1, 5 is not included because we have a hole. However, if we look at the graph of our second subfunction, 5 is an included value. So we do not see any hole in our second graph. So therefore, according to the rule, so y is a range of the main function. So y is a range of the main function if it is included as a range of at least one of the subfunctions. So at least one of the subfunction. So here f of 2 includes 5, and then f of 1 here does not include. So since f of 2 includes 5, 5 is part of the range. Okay, so I hope this is clear to everyone. So example. So determine the domain and the range of the following piecewise function, and then write it in interval notation. So we can use VLT again. We can use VLT and HLT to check for any discontinuities. So if there are any holes or if there are any gaps in the graphs, then we can use the VLT and the HLT to check these discontinuities. So if we use the VLT, so we know that for the domain of this piecewise function, if we use the VLT, so the line, the vertical line, will start from the negative infinity of x. So here is our negative infinity of x. So why do we know that this starts, that the domain starts from the negative infinity? So if we look at the line, if we look at one of the graph of the subfunctions, the graph is pointing towards the negative infinity of x. It is progressing towards the negative infinity of x. So therefore, this will start from negative infinity, and also the end point of this graph is an arrow. So that's why it is from negative infinity. So if we move our vertical line test, we will see that there is a hole at x is equal to 0. So since there is a hole, we know that 0 is not included. But before you conclude that 0 is not included, take a look at the other graph. So if there are other graphs that shares the same value of x, so x is equal to 0, then tignan nyo din. So examine also whether the other graph does not include 0 as in its domain. So if it is a hole also in your second graph, then you may conclude that 0 is not part of your domain. So if we continue our vertical line test, you can see there are no other discontinuities. We don't see any holes or any gaps in our graph. And then our second graph, so the graph of our second subfunction, is progressing towards the positive infinity of our x-axis. So we can create here a union. So the second graph starts from 0, where 0 is not included, towards positive infinity. Okay. So for the notation, for the set builder notation, this is how we represent our graph. So this one. So this is the interval notation. This is our set builder notation. So how about the range of our graph? So in determining the range, we can use the HLT as our guide. So the horizontal line test. So we know that the range will start from the negative infinity of y. So again, because our graph, if we examine one of the graph of the subfunction, it is progressing towards the negative infinity of y. So therefore, we know that the range will begin at the negative infinity. And if we move our horizontal line test, so we can see here that our two subfunctions share the same value of y. So let us write here the range. So for the range, again, we begin from negative infinity of y, and then at y is equal to, so this is negative 1, negative 2, so negative 3. At y is equal to negative 3, there is a hole. So for our second subfunction, there is a hole at y is equal to negative 3. However, if we look at our other subfunctions, in f of x is equal to x, there is no hole. So 3 is included in one of the subfunction. So therefore, 3 is included in the main function. So therefore, we don't need to write here 3, and then we don't need to write here 3. So let's remove this one. So if we continue our horizontal line test, so our graphs stops at y is equal to 0. So therefore, we will end our range to 0. So 0 is not included because we have a hole in y is equal to 0. So this is y is equal to 0. However, since there is a hole, therefore 0 is not included. And in the writing convention of the domain and range, we use a parenthesis to denote not included values. So here is the range, and this is the set builder notation. So therefore, for the set builder notation of the domain, so we know that the domain is the element of real numbers except x cannot be equal to 0. So x, we do not have a value for our function if our x is equal to 0. And then for the range is y such that our y is a value that is less than 0, because we do not have any values above y is equal to 0. Okay, so example number 2. So look at the graph. We look for the domain and range of our sample piecewise function. So for the domain, if we look at the domain of our example number 2, so we begin from this side. So this is our x, negative x, this is our positive x, this is positive y, and this is negative y. So if we look at the domain, so here is our, we have 3 graphs. So therefore, there are 3 subfunctions. So let's let this red graph as our first subfunction. So if we look at our subfunction number 1, so f1, and then this is f2, and then this is f3. If we look at this subfunction number 1, this is progressing towards the negative infinity of x and y. So if we can continue the line, and you'll notice that this will progress towards the negative infinity of x and y. So this will continue towards the negative infinity of x and y. So therefore, for the domain, we will begin at negative infinity. And then if we move towards this point, if we sketch a vertical line, so our subfunction number 2 and subfunction number 1 shares the same x value, which is negative 2. So this is negative 1, negative 2, negative 3, negative 4. So they share the same x value. So one of the subfunction includes negative 2, one of the subfunction does not include. So since 1 includes negative 2, therefore negative 2 is part of our domain. So again, if we move our vertical line, so you'll notice as we reach x is equal to 2, so here, this is 1, this is 2. At x is equal to 2, there is a hole. So here. So therefore, since in this subfunction, this does not share, we do not see any sharing of the values x is equal to 2 in this section of the graph. Therefore, since here in subfunction number 2, 2 is not included, we write here 2 where 2 is not included, and we create a union. So now if we look at this part from 2 to 3, there is a gap. So if we draw a vertical line test between 2 and 3, there is a gap in our graph. So therefore, we will move on to the part of the graph which has a value. So at x is equal to 3, so in this section, x is equal to 3. So 3 is an included value, so we have a shaded circle, so therefore 3. And then, since we have here an arrowhead, we know that this is progressing towards the positive infinity of x. And for the range, so for the range, we will start from the bottom. So we have here arrowheads, so therefore the range begins from negative infinity. So at this point, if we draw a horizontal line test, at this point, graph of subfunction 3 and subfunction 1 shares the same value. Both of them includes 1, y is equal to 1. And then at this point, y is equal to 2 is not included. So therefore, we write here 2 and then we use parentheses. So if we use parentheses and then if we have other values, we create a union of values. So from y is equal to 2 until this point, we have a gap. So to continue the value of our range, let us examine our the graph of subfunction number 2. So subfunction number 2, there is a hole also. However, some part of the subfunction number 2 includes this value. So therefore, so what is the value of this one? So this is y is equal to 4. So therefore, our range is from negative infinity to 2, union 4 to 4. So to demonstrate it, to write it in set builder notation for the domain, x such that x is less than 2 or x is greater than 2. And then for the range, y such that our y is less than 2 or y is equal to 4. So answer these practice exercises. Determine the domain and range of the following graphs of piecewise functions. Write it in interval notation. So you may pause this video and then resume watching to know the answers. So for number 1, we have here 4 subfunctions. So this is our subfunction. So let's say this is S1, this is S2, S3, and then S4. So where did our function start? So if we examine, so from negative infinity of x, so if we look at it, the end point of our graph here is a hole. So our domain will start from this point. So this the corresponding value here is negative 6. So the domain will start from negative 6, where negative 6 is not included since we have here a hole. And then if we move towards this section, so where x is equal to negative 2, so negative 2, so we need to identify or determine whether negative 2 is an included or not included value, because there is a sharing of values here. So since one of the graphs, one of the subfunction includes negative 2, then 2 is part of the domain. So if we move now to this section, the same situation happens. So they share the same value of x, where x is equal to 2. So since one of them includes 2, therefore 2 is included. And then if we move now to this section, the same situation again. So for x is equal to 5. And then if we move now to our endpoints, so the endpoint here, so this is positive 7. So the endpoint here is x is equal to 7. But we have a hole at x is equal to 7. So we need to know whether there is a sharing of values or none. So if there are no sharing of values and there is a hole, therefore the corresponding value, which is x is equal to 7, is not included. So our domain is from negative 6 to 7, where 7 is not included. So on the other hand, if we look at the range of the values, so we need to examine from bottom, from the negative y to the positive y. So where is our graph located? So if we look at this one, so the graph begins from y is equal to negative 1. So although in this section, so if you look at this one, so there is a hole in negative y is equal to negative 1, there is also a hole in this section, and another hole in this section. But if we look at this part of the graph, it includes negative 1. So therefore, negative 1 is an included value. And then, progressing, so at this section, if we look at this section, so there is a sharing of value, so 0, 0. So both of the graphs here includes 0, y is equal to 0. And then if we move again to this section of the graph, so another graph here, so 3 graphs share the same value of y, which is y is equal to 1. So all of them includes 1. And then if we look again at this section of the graph, so one of the graph does not include y is equal to 3. So y is equal to 3. So our subfunction 1 does not include y is equal to 3. However, our subfunction 2 and then subfunction 4 includes y is equal to 3. Therefore, 3 is included. So now, if we look at this section, so subfunction 2 and subfunction 4 share the same y value, so y equals to 4, wherein 4 is included to both of these subfunctions, so therefore 4 is included. And then finally, if we reach the end point of our graph, so y is equal to 5, so y is equal to 5, so 5 is not included because we have a hole in y is equal to 5. So therefore, our range is from negative 1 to 5, where 5 is not included. Okay, so this is our, what do we call this? This is our set builder notation. So x such that our x is greater than 6 but less than 7. So greater than 6 because 6 is not included, and we have values for x greater than 6, and then less than 7 because our graph ends at x is equal to 7, and then 7 and 6, negative 6 are not included. For the range, we have negative 1 is included, and 5. So for the set builder notation, y such that our y is greater than or equal to 1, because negative 1 is included, and then less than 5 because 5 is not included. So here is our y is equal to 5. Here is our y is equal to negative 1. And for our last example, so for the domain, so if we look at this one, so this is negative 7, this is 7, this one is also 7, and this one is negative 7. So this is the negative infinity of y, this is y, negative x, and this is x. So if we look at this graph, so we started from negative 7, where negative 7 is not included. And then, if we look at this part of the graph, we have a hole, and there is no sharing of points. So therefore, at this point where x is equal to 4, x is equal to 4 is not included. So we use parentheses and then union. So where did the other graph begin? So our second graph started from x is equal to 5, where 5 is included. And then it ends with 7, where 7 is not included since we have a hole in our graph. For the range of our function, so we begin from the negative infinity of y. So if we look at this one, the end point of our second graph is included value, so bounded. So you have a bounded value, so it begins with negative 7, so the range begins from negative 7. Since this is a shaded value, then we use a bracket. And then if we look at this one, at y is equal to negative 5, so negative 5 is not included value, so we write it here. And since it is not included, we use parentheses. So there is a gap in our graphs. So where did our other graph, our other subfunction begin? So here, it started from y is equal to negative 2. So therefore, we need to create a union and then begin from y is equal to negative 2. And then we need to use a bracket because negative 2 is an included value. So if we look at the graph, we don't see any holes in this part. So therefore, negative 2 is included. So in this part of our graph, we see a hole. However, other parts of the graph includes this value, y is equal to 1. And then the other endpoint of the graph is 7. However, since we have a hole in our y is equal to 7, therefore 7 is not included. So here is the domain range of our second problem. So the domain is from negative 7. So this is negative 7, where 7 is not included since we have a hole, until 4, where 4 is not included, union with 5, where 5 is included, to 7, where 7 is not included. So for the set builder notation, we use the following. So x, such that our x is greater than negative 7 but less than 4, or x is greater than or equal to 5. This is greater than or equal to 5 but less than 7. For the range of our piecewise, so we started from negative 7, where negative 7 is included, to negative 5, where negative 5 is not included. Union, since we have here a gap, we need to create a union. So union, so this point here is it started with negative 2, where negative 2 is an included value, and up to 7, where 7 is not included. So for the set builder, we have y such that our y is greater than or equal to negative 7 but less than negative 5, or y is greater than or equal to negative 2 but less than 7. So if you have any questions, you may send it via PM in Messenger. So thank you for listening. So in our next video, we're going to discuss how to model a function and some of the applications of piecewise defined